Let's talk about regular languages and regular operations. Specifically, we're going to look at the union operation and what closure under union means for regular languages. First, let's remind ourselves what union is. So, if I have a Venn diagram, and we're going to call this A, we're going to call this B, then the union of A and B is everything that's in A and everything that's in B. So that's the union. It may also be the case that they intersect. Let's call this A prime and this B prime. Then again, union is everything in A and everything in B. And again, we have the union. So let's look at a string example because we're about strings. So let's say that language A double prime consists of the strings A, AA, and AAA. So this is a finite language. And let's say that language B double prime contains the strings B, BB, and BBB. Okay, and then here's my universe. We'll draw the universe. And then everything that's not in A and B is out there in the universe somewhere else. So AB, AB, this is out here. Okay, so then what is, oops, try it here, A double prime union B double prime? It's going to be everything that's in A double prime and everything that's in B double prime. So A, AA, AAA, B, BB, BBB. Okay, so this is the language A double prime union B double prime. Okay, let's look at another example. Let's look at a infinite language example. So let's say that language A is W such that W has an odd number of A's. Okay? And let's let language B be W such that W has an even number of B's. Let me go ahead and define that sigma for both languages is AB. Okay? So now we're interested in finding A union B. Okay? Well, it's going to be anything in A and anything in B. So W such that W has an odd number of A's, or, I'm going to make this in uppercase just to make sure we're very clear that it's an or W has an even number of B's. Okay, so let's draw a picture to represent this language. So let's start off with our universe. Let's put our universe here. Universe of all strings over the alphabet AB. Okay, and let's put an A here. So A is going to be all of these strings here. And let's choose some, so anything with an odd number of A's. So A, BBB, AB, BA, okay. Also ABB and just A. These are all in A. And then let's put in language B here. Notice I immediately included some of the strings in A, such as ABB. because ABB has two B's, so it has an even number of B's. So this string is also in the language B. Also, the string A has an even number of B's, since we typically say that 0 is even. So these strings would both be in the language B. Some other strings that are in B but not in A would be BB, ABBA. Okay, so we have some strings. We could also do BBAA. That would also be in the language B. And then let's put one out here in the universe, AAB. Okay, so this one's out in the universe, not in either A or B, because it has an even number of A's and an odd number of B's. So it doesn't satisfy the conditions for it to either be in language A or B. Okay, and then here we know the union AB. Let me try to get this as close as I can. Okay, it's going to be, so any gappage between the circles is just from the pen, not intentional. Okay, so that's going to be A union B, is this language here. All right, so union gives us an interesting property, and that is that regular languages are closed under union. So let's remind ourselves what a regular language is. So a language is regular if and only if some finite automaton accepts it. Okay? So I know a language is regular if I can make a finite automaton that accepts that language, and if I have a finite automaton that accepts a language, it must be regular. Okay, and so we also stated that regular languages are closed under the union operation. Okay, so what does this word closed mean? Okay, it means if A, so language A, is regular and language B is regular, then A union B, this language, must be regular. Okay? So that's what closure means. It means if I start out with two regular languages and I take the union, the resulting language is regular. Okay, so we would like to see a proof of this, right? We don't like to take anything just on faith. We like to see proofs. So we're going to do a proof by construction. Okay? And actually, instead of doing a generic proof by construction, we're going to take an actual example and take two regular languages and show how this construction would work. And then I'm going to state that you can generalize this out to any regular language. Normally, we can't start with an example and generalize it, but the example is just to show you what this proof actually looks like in action. Okay? So let's go back to our previous A and B languages. So again, we have A is W such that W has an odd number of A's. And we also have language B, so W such that W has an even number of B's. Okay, so here's my two regular languages to start off with. Since they are both regular, this means that there is some machine, MA. So we have some machine MA. Oops. Let me make some room here. 1 second. Let's get rid of this. Okay. All right. So I have some machine MA such that the language of MA is A. Okay? that will be my proof that A is regular. And in just a second, we're going to make a machine MA that actually does accept A. And also, since I'm saying that B is regular, it must be the case that there's some machine MB such that the language of MB is B. Okay, and again, we're going to make a machine to do that. Then we're saying that if L is my new language, is going to be equal to A union B, it must be the case that there is some machine M such that the language of M is L, or is A union B. Okay, so this M right here, this is what we're going to construct. And we're going to construct it using machines MA and MB. Okay? So, first, let's make our machines MA and MB. So let's make MA over here. Alright, so this machine needs to accept A. So we need to accept whenever we have an odd number of A's in the string. Okay, so really what we need to keep track of is whether we've seen an even number of A's or an odd number of A's. Alright, so let's make two states. I'm going to call them even A and odd A. Okay, and I want to accept when I've had an odd number of A's, so I'm going to go ahead and make this one final. Alright, where do I start off? Well, if I haven't read anything yet, it means I've read 0 characters. And if I've read 0 characters, it means that I've read 0 A's. And we've said before, 0 is even. So when I start out my machine having read nothing at all, I'm going to start off in this even A state. Okay, so when I'm there in even A, if I see an A, I need to transition over here to odd A's. Right? No matter how many A's I've seen, whether it's 0, 2, 4, or 6, if I see one extra A, I'm going to have an odd number of A's. Whereas if I, let me add the A there on that transition, there we go. Whereas if I'm in state even A and I see a B, I haven't changed my number of A's, so I'm just going to stay there. Alright, so that's 2 transitions, one on each symbol for that state, so I'm done with that state. And let's go to the odd A. If I'm in odd A and I see an A, I now have an even number of A's. And if I'm in odd A and I see a B, I just stay put. Okay, so there's my machine MA. And you can verify for yourself that it will accept whenever the string has an odd number of A's. And let's build MB. It's going to be pretty similar. In this case, we're just checking for even B's. So we want to keep track of whether or not we have odd B's or even B's. So let's make our states to reflect that. We're going to make a state called even B. And we're going to make a state called odd B. And when do I want to accept? I want to accept when I have an even number of B's. Right? I also start off with an even number of B's, right? Same argument that we had for A's. If I have 0 characters read so far, I've had 0 B's, and that's an even number. Alright, so if I'm in state even B and I read an A, well, nothing's changed for my B's, so I stay put. Whereas if I read a B, I've now seen an odd number of B's. If I'm in state odd B and I see an A, again, nothing's changed for my B's. But if I see a B, I need to flip over to the even B state. Okay? So here's my 2 machines. Alright. So now what we need is actually, we need to find that machine M. This guy right here. So what do we need to do? We need M to simulate both A and B. Okay, we need to keep track of where we would be in machine A and where we would be in machine B. The reason that we can't just say, okay, well, let's just run the string on machine A, and then if it doesn't accept, we'll run it on machine B. The problem with this is our input model is that characters are basically consumed as they're read. It means we can't go backward on our tape. We can't say, well, I read all of that string and I didn't accept, so let me read it again. Those characters are gone. We can't go back. So instead what we need to do is create a machine that actually keeps track of where we would be in machine A, MA, up to however many characters we've read, as well as where we would be in machine B up to however many characters we've read. So we're going to simulate both machines simultaneously. And then if either machine accepts, we're going to accept. Because remember, A union B means if it's accepted by MA or if it's accepted by MB, we're going to accept. Okay? Notice this is not exclusive or. It could be accepted by both machines, in which case we want to accept. So how do we do this? Well, we've seen Cartesian product, and that's actually what we're going to use. We're going to make a Cartesian product of the states of MA and MB. And this way we'll be able to say, if I've read this many characters in the string, I could be either in this state of machine A, or I could be in this state of machine B. And that's actually going to work for us. Okay, so let's build this. Remember, the Cartesian product says choose one state for machine A and choose one state for machine B. And we're going to do this for every combination. Okay, so let's choose, for convention, I'm going to write the state of machine A on top, just so we can be clear. So machine A has a state called even A, and machine B has a state called even B. So I'm going to combine these together into one state. So this is machine M. Okay. Machine A also has a state called odd A. That's not very O looking. Let's take care of that. All right. Okay, we also have a state called odd A in machine A, and let's pair that with even B. Okay, so now I have both combinations of states from machine A paired with one state from machine B, right? So now I need the other set of combinations. So let's do even A paired with odd B. And then let's do odd A paired with odd B. Okay. So you can check that I now have every combination of states from machine A and machine B, right? Yes. Okay. So now we need to simulate what we would do on machines A and B. So first question is, where do we start? If we look back, both machines, say machine A started when we were in state even A, and machine B started when we were in state even B. So we want M to start off when we're in state even A, even B. Okay, so this is going to be our start state. Okay, and what do we do in that state? If I see an A, so I had an even number of A's and an even number of B's, and I see an A, the number of B's hasn't changed. I still have even B's, but I now have odd A's. So we want to go to the state odd A, even B. So I go to this state on an A. Okay, if I'm back in that even A, even B state and I see a B, I still have even A's, but now I have odd B's. So I go here. Okay, so that's all the transitions for that state. So let's go to the state even A, odd B. If I see an A, I still have odd B's, but now I have odd A's as well. Whereas if I'm in even A, odd B, and I see a B, I still have even A's, but now I have even B's as well. So I go here. Okay, that's all the transitions for that state. Let's go to state odd A, even B. So if I see an A, I'm going to go to even A's, and the number of, or the B's hasn't changed. So I'm going to go here. And if I'm in odd A, even B, and I see a B, then I need to change from even B's to odd B's without changing the A's. Okay, so that's all the transitions for that state. Last, I'm in state odd A, odd B. If I see an A, I'm going to go to state even A, odd B. And if I see a B, I'm going to go to state odd A, even B. Okay, and that's all the transitions for that state. So now we have all of our transitions, and we're simulating both machines, and now we need to know when should M accept a string. Well, it should accept a string if either A or B, if either machine A or machine B accepted. So when does machine A accept? It accepts whenever we're in the state odd A. So if I see an odd number of A's, machine A is going to accept. Whereas machine B accepts whenever I see an even number of B's. Okay, so let's go back to this machine. We want to accept if we have an odd number of A's. So here, let's make this a final state. Okay, so we would accept, this would accept when machine A accepted. I would also accept, machine A would have also accepted here when I had an odd number of A's. Machine B is going to accept whenever I have an even number of B's. And notice this state here is already final, okay, because we made it final because machine A would have accepted there, and we're going to keep that. Or here, we have an even number of B's here in the start state. Okay, so notice here that the only one we don't accept on, the only state we don't accept in, is when we have an even number of A's and an odd number of B's. Okay, so let's think of some of these string examples that we came up with in our diagram and why that's a great thing to do. We said that we should accept on string A, B, B, B. A, B, 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 right? Because this was in language A, so it's going to be in it's going to be in L, which is A union B. So here I read, if I were to read through, I start off in state even A, even B. I read in A, I'm going to go to odd A, even B. I read a B, I'm going to go to odd A, odd B. I read a B, I'm going to go to odd A, even B. And I read a B, and I'm going to go to odd A, odd B. So I'm now in state odd A, odd B. I've read all of my string. I'm in a final state, so I accept. So this is good. That's what we wanted to see. Without running through the states and some of the other strings, I'm just going to write them down here. We can verify to ourselves that we should accept on these. So AB, this is going to put me in odd B, odd A, right? And that's a final state, and that's good. We also had A, B, B. Okay, so odd A, even B, and that's the final state, so that's good. BB, that's going to put me in even A, even B. That's a final state. Good. How about ABB, A? Same thing. It's going to be an even number of B's and an even number of A's. That's a final state, so that's great. All right, and then our string that we had that was not in the language was AAB. Okay, so this is going to give me an even number of A's and an odd number of B's. And we look, that's not a final state. So that one's not going to be accepted, and that's what we wanted, right? That was not in the union. Okay, so this shows us that we have constructed M is in fact a machine. So what do we have? We have that the language of M is equal to A union B. Okay, so that's what we wanted. M is a finite automaton. Therefore, the language of M is regular. Okay, so we just showed that A union B is regular. Okay, and with a little bit of extra work, you can show that no matter what machine you're starting with, really it's not extra work, it's just extra formality. You can show that as long as you have two regular languages, therefore you have two machines, you can do this construction that we did, this product construction, and you will end up with another machine. And this machine will be the language of the union of those two languages. Okay, so this shows closure under union for regular languages. Okay?